So, Professor Peoples, I hear you saying, if we've been solving these systems of equations in the last section, we found systems where we had a dependent solution and systems where we had a inconsistent system. How do we know when that's going to happen here? Well, let's try it out. Let's say we're going to use this system of equations. We want to add together and let's say eliminate x. So we're going to take line 1 and line 2, line 1 and line 2, and we're going to take, let's try this time, -3 times everything in line 1, right? Because if we had a -6 up here, -3 times 2 would give us -6, and -6 plus +6 gives us 0, so we'll get rid of the x. Plus line 2 to get our y isolated. Let's see, we're going to try and do that. So let's take everything in equation 1 by -3. So we're going to take -3 times 2x minus y and set that equal to -3 times 3. And what do we come up with but -6x plus 3y equals -9. There's a y there, missed that. And here we've got positive 6x minus 3y equals 9 in equation 2. Right? So we take line 2 and we put that right here and we add these things together. We're going to get 0 plus 0 equals 0. So what values of x and y is that true for? Well, that's always true. Always. See if I can spell always with any manner of efficiency here. Always true. Yes, there it is. All right, well, if that's the case, when you end up with this arrangement, where you end up with a certainly 100% true equation on both sides, we say that this is a dependent system. Right? And if you remember how we wrote the solution, whenever we had a dependent system, we tried to express it in such a way that we had x and then replaced y with some expression containing x. So let's take line 1 right here. It's easy enough in line number 1 to isolate y, because we have 2x minus y equals 3. So if we take away 2x from both sides, we get y is equal to -2x plus 3. And dividing both sides by -1 to eliminate that negative right here, that's a -1, we're going to get y is equal to 2x minus 3. And so our dependent system solution would look like x, comma, 2x minus 3. All right, so far so good, you say. Let's try another, though. This time we're told to solve the system of equations by the addition method. Should we come up with another dependent solution? Well, I'm going to pause for a second. I'm going to let you guys try it out yourself. All right. If you paused it and tried it, you might have come up with the following solution. Let's say we're going to take line 1, line 2 right here, and to combine these together, I want to get rid of x this time, so I'm going to multiply -2 times everything in line 1 and add that to line 2. I always write out my plan here ahead of time. It's just a very good organizational method. So let's take -2 times everything on the top equation. That's 2x minus 3y is going to equal -2 times 9. Rewrite that, so we're going to have -4x plus 6y equals -18. Interesting. Okay, -18 there. This is almost beginning to look like our last setup, right, where we got 0 equals 0. Will that happen here? Well, no, because when we add the second equation, 4x minus 6y equals 4, and combine these two equations, we come up with 0 on the left, but on the right we come up with negative 14. Well, clearly 0 does not equal negative 14, so what conclusion should we reach? Well, in this case, we're going to have to say it's an inconsistent system. Inconsistent system. And the conclusion that we would reach here is that there is no solution at all. Okay, upping our game in the next video.